Okay, so here is a first order linear differential equation. I'm going to solve it two different ways, just to emphasize that there are multiple ways of solving these problems. One way is a good way. That is, I think we should treat this as a first order linear equation and do integrating factors. But for this particular problem, we can actually treat it as a separable equation. I'm going to do it both ways. The first one is going to be integrating factor, the integrating factor method here. The integrating factor is mu of t is equal to e to the power of the coefficient on x. So that's just going to be t. And so this is e to the power of t squared over 2. Okay, I'm going to multiply both sides by the integrating factor. You get x times e to the t squared over 2 prime is equal to e to the t squared over 2. And we multiply that by t. And now we take the antiderivative of both sides. So the antiderivative on the left-hand side, of course, is the easy one. This is e to the t squared over 2. And this is equal to the antiderivative of t e to this t squared over 2 dt. And I'll go ahead and do this integral out kind of explicitly. This is a good u sub problem. So u is going to be equal to t squared over 2. And then du dt is equal to t. And so the antiderivative on the right hand side is going to be e to the power of u du, and this is just going to be the antiderivative, of course, is just e to the u, so that's e to the 1/2 t squared plus c. And so this tells us that x of t, so now this is, let me just bring this down here, this is x of t e to the t squared over 2. When I divide both sides by e to the t squared over 2, you get 1 plus ce to the t squared over 2. Okay, that's method 1. Method 2 is to treat this as a separable equation. Okay, if I treat this as a separable equation, I first need to get all of the t stuff on one side and all of the x stuff on one side. Now, since the coefficient on x is equal to this non-homogeneous term, notice I can write this as x prime is equal to t times x minus 1, and I can divide both sides by x minus 1, and I get 1 over x minus 1 dx dt is equal to t. Okay, the left-hand side, okay, so it's a separable equation. This is very similar to the one we did before. The left-hand side is the derivative with respect to t of the natural log of x minus 1, and this is equal to t. Okay, we take the antiderivative of both sides. We get the natural log of x minus 1 is equal to t squared over 2. Okay, we raise both sides up, plus c, the arbitrary constant. We raise both sides to the power of e. We get the absolute value of x minus 1 is equal to some arbitrary constant a. That's really e to the power of c, but that's an arbitrary constant, so we just write a times e to the t squared over 2. And remember, these absolute values are just represent another arbitrary constant, either a plus or minus 1, and so x minus 1 is just equal to a times e to the t squared over 2, where we're just absorbing that plus or minus 1 into the a, and then we get x of t is equal to 1 plus a e to the t squared over 2. Okay, and maybe even you like this method a little bit better because we didn't have to do this integration there. We didn't have to do the integral of t e to the t squared over 2. Okay, so in this particular problem, since the coefficient on x is equal to this non-homogeneous part here, we could do separation of variables. Okay, whenever you have a first order linear differential equation, you can always do this as an integrating factor, so you can always do it as we did on the left hand side, but you can't always do it as a separable equation. But I just wanted to show you two different ways of doing it.